happy to have the last talk with Stefan Großkinsky, and he will tell us about size-biased diffusion and limits and the inclusion process. So Stefan, thank you, and the floor is yours.
Thank you. Okay, thanks a lot for the invitation. So I'm going to talk about joint work with Paul Kleban and Simon Gabriel, which were both at Warwick, and I'm going to skip this some part of the talk due to time, but still there was another collaborator doing something stationary. I will mention that. So it's going to be mostly about dynamics here. So what is I'm looking at the interacting particle system. So we have a lattice lambda of L sides. We put n particles on the lattice. Eta x is the number of particles on side x. There can be any number of particles on a given side, and they jump according to a continuous time Markov process with rates that have a spatial part. This is pxy that gives you the conductivity essentially on the lattice. I just draw this one dimensional here for simplicity, can be anything at this point. And then there is an interaction part, which is a c. That is the rate depends on the number of particles on the departure side and the target side, and nothing else. Okay, good. You can think of this as a kind of interaction kernel. We had just had a talk about coagulation, which is a very similar interpretation. So we only, in this talk, only always one particle moves. So we essentially have clusters and they exchange monomers only, but with the rate c. The interesting part of the rate is c. Good. This would be the generator of this process. And you want to look at a spatially homogeneous situation. So essentially the P is not going to be important. In the second part of the talk is even going to be a complete graph. Okay. So the most interesting thing is the interaction part of the rate. And for the inclusion process, which is a process I'm mostly focusing on here, it has a particular form. So it's a product kernel, essentially. And there's also a breakup part, if you think like this. So D is kind of the rate at which a single particle of a cluster with eta x particles moves to a random location, okay, whether there is mass or not. Okay, so this you can think of breakup. And this is kind of exchange of monomers between clusters. And there's also another biological interpretation of this model in terms of Moran models, and then you have lambda is a type space, and this is a number of individuals of a certain type, but I'm not going to refer to that much, okay? But in the biological application, it's very natural to make this d small, so because it's kind of a mutation rate, and this is often small compared to a resampling rate. The resampling rate will be the prefactor of this guy, it's 1, so you just set the time scale by this. And then you have another process, which I will refer to the breakup process, and this is kind of slow compared to the exchange of monomers between clusters. Okay, then this model gets even more interesting with gelation happening even at instantaneous gelation if you add another power here, but I'm not going to talk about this, but this is kind of what we would like to understand in the future. Okay, so make this kernel from the product kernel more higher order of homogeneity here. Okay, and by the way, Kaprivsky and Redner, because they were mentioned before, studied coagulation, but they also studied this kind of thing and called it exchange-driven growth, where clusters only exchange monomers, and they studied this kind of thing holistically. And it's understood what should happen. Good, so we want to make these small, so this is the breakup rate. If it's order 1, a typical stationary configuration looks nothing spectacular. There's no really clusters, it's just a homogeneous distribution of mass. If it becomes small with the system size, so we are going to look at a hydrodynamic limit where the number of lattice size goes to infinity and the number of particles as well, before converging to a fixed density, mass density on the lattice. And if this dB is becoming small in the limit, then you see clustering happening. And the kind of critical rate at which it becomes small is 1 over L. Then you have say an order 1 number of clusters that have a particular interesting hierarchical distribution. If it is decays slower than that, you will have a diverging number of clusters, and if it decays faster than that, you will only have a single cluster in the typical stationary configuration. Okay, and good. So outline is I will quickly tell you what happens at stationarity, and then talk about the dynamics. So these results are more general, don't only apply to the inclusion process, and they work on any spatially homogeneous system, also on the lattices. And the second part only works on the complete graph and for the inclusion process at the moment. Okay, and the inclusion process has been studied a lot also in other types of scaling limits, in particular this scaling where you have only a single cluster. This cluster then moves on a fixed lattice has been studied in the context of metastability a lot. Okay, just to mention this on the side. So we are going to look at the inclusion process. So you have, it's part of a class of interacting particle systems where you have an explicit formula for the stationary distribution, and it's a product distribution. And this is even, for the inclusion process, even, you know, even more than that. So you have an explicit form for the stationary distribution here. As I said, it's a product of stationary weights, and you have an explicit formula for the weights. And what is even better for the inclusion process than usual is that you even have an explicit formula for the partition function, so the normalization constant of this measure when you fix the total number of particles. This is usually not the case, okay? So, but here we have this. So essentially, we have to study this normalization factor in the hydrodynamic limit and the thermodynamic limit, and it's simply an asymptotic analysis you have to do of this for the inclusion process at stationarity. And what is interesting here is you want to study the clustering of the particles, and if you look at since they cluster, if you look at a fixed lattice size and you send Ln to infinity, it will typically be empty because the mass is clustering on the vanishing volume fraction, so you won't see anything. So you have to kind of look at your particle configuration in a particular way. One usual way is to simply order it. So the highest, you look at the highest cluster first, and then the lower ones, and then obviously you see some mass here, but then you have lost the spatial information. And another approach, which is a bit more practically useful, is a size-biased sample. So you don't pick a site and look at it at the occupation, but you pick a particle uniformly, and then you look at the occupation number where this particle sits. Okay, so this is you could often call size-biased sampling, and you can do, yeah. This is, I explain it here in words how you can do that, right? So and then you can see the clustering of the particles in this particular sampling of your configuration. I'm not sure if we will need to log. So, and then of course what we're going to do is, okay, so this is a size-biased thing. So I have a configuration, you do a size-biased resampling, and then I renormalize everything by the total number of particles. So this will sum up to 1. So it's on a simplex and gives me the distribution of mass if I do a size-biased sample. And then you can derive what happens to this in the limit as NL goes to infinity in a way that we have a constant density and this breakup rate goes to 0. And the first statement simply says, if I don't size bias anything, I just look at k fixed size, they will be empty because I have a clustering phenomenon. Then if I look at size bias sides and my clustering rate decays, but not as fast as 1 over L, then I will have clusters of size, typically size 1 over D, and they will have a distribution like IID exponentials. Okay, so essentially good. And the most interesting case is when my breakup rate scales exactly like theta over L here, for example, and then you will have the mass distribution will be given by the Chem distribution or the Poisson-Dirichlet distribution. If you look at the ordered version of this partition of mass, okay, I can explain this quickly if you haven't seen this. So what is this Chem distribution? So it has a parameter theta, but if theta is 1, this is particularly simple. So you simply take your total mass, which is the interval 0 to 1, you take a uniform random variable in between and you break up first part of mass. This is the size of your first cluster. And then with the remaining stuff, you do the same. You take a uniform random variable and produce the size of the second cluster. And this is this stick-breaking construction of the Chem distribution. And this is exactly how your mass is distributed at stationarity for the inclusion process. And then if this thing, this includes, by the way, the parameter 0. So if your breakup rate is essentially decaying so fast that it scales to 0, then you only have one large cluster here. So the Chem 0 distribution includes the situation where you have only one large cluster. And if this decays even faster, then not only do you have one large cluster, but all the particles are in one cluster and there's nothing outside it. So if this guy goes to 0 even a bit quicker. Good, so this is mostly the stationary results here. And the interesting part about this is they don't only apply to the inclusion process, but you can generalize, obviously. And the most significant thing is how do the stationary weights in this is again the stationary distribution for the zero range, for the inclusion process. L is the volume, N is the mass, and we have these weights, and we had an explicit formula. In general, you don't need an explicit formula, but you need to have some decay condition. Okay, and that essentially tells you that these stationary weights should decay like 1 over N and times a parameter theta. And if this is the case, so don't really look at this in too much detail, then essentially you have the same behavior for any kind of particle system that has such stationary product measures. Okay, and you can even have come up with examples where not all the mass is clustering, but where you have some mass, some dust in the background of the system that remains there, and the part of the mass that is clustered will be Poisson-Dirichlet distributed. Okay. For the inclusion process, this rho c, which would be this critical density or the background density, this would be 0. Okay, so everything clusters in the inclusion process. But you can cook up other examples that have this structure, that have the similar behavior for the condensed phase. Good. So that's what I want to say about the stationary dynamics. I skipped the proof and the pictures, and we move to the dynamics. Okay. So now we look at only the inclusion process, and we look on the complete graph. So all the clusters essentially are connected, and they can directly exchange particles. Good. So the P is gone here in the generator. And now, how do you want to study the dynamics of this? So you can look at empirical measures where you essentially put a Dirac measure at any location where you have a cluster, okay, and you bias it with the size of the cluster, and that gives you an empirical measure how you can study this distribution on actual space. And then, okay, what you do, so this is, you test it with a test function, so you get a simple average of a test function h here, and then you act with the generator on this. The generator is acting on the configuration eta, right? So how does this observable that you look at change under the dynamics? And you see that the inclusion part of the dynamics, or this resampling part with the product kernel, due to symmetry gives you 0 at this order, and there's only a part remaining that comes from the breakup. Okay. And now, if you want to send Ln to infinity, if you scale everything correctly, I put an L over L here already to see that this 1 over L sum y will converge to the integral here, and the 1 over n sum x times eta x will converge to this expectation under this mu eta measure. And I'm sorry, this is a typo here, this should be an eta. Okay, so essentially this term converges to nicely in the limit. And all the sigmas here should be etas, I'm sorry. So this is what you get, say, to first order. And if you want to study the fluctuations of this process, you will have to look, this is a standard thing in the interacting particle systems scaling limits, look at the Carré-Duchamp operator, which is essentially a quadratic thing, okay? So I'm not taking this test, I take the square of this test function and I act with L on it, and I subtract the normalization, and you can compute it. Good. So what you get in total as if you take you have a random measure, mu t, that evolves in time, okay? So this thing converges actually in the hydrodynamic, now the thermodynamic limit, in distribution to a measure value process where mu t is a random measure. If you test it with a function h, it's a simple diffusion process, okay? And I just essentially derived these two parts of the diffusion process where this is the drift will be given by this, it's called mutation part. If you think about this as a population dynamic, it shows up a lot there. So this is a standard, did I write it here? It's a Fleming-View process that has been studied a lot in population dynamics, this type of measure value process. And this is called mutation, and this is called the resampling part here. And this is given by a martingale where we know the quadratic variation. Okay, so this is, in fact, this process is known. So it here occurs, in fact, introduced it even in 81 with a completely different setting. So they looked at the distribution of mass on the ordered simplex and introduced this diffusion on this ordered simplex and called it infinitely many neutral alleles model. And then later realized, okay, there are several technical problems with how to define this operator, because if you look at it, it doesn't seem to conserve the first moment here. So, but you can fix it, but it's kind of technical. And later they realized, okay, there's an equivalent measure valued formulation of this model that is a standard model in population genetics, and it's actually exactly this one. So the inclusion process, the scaling limit of the inclusion process dynamics has been known for a long time in principle. So what we were interested in is now we want to look at other scalings, not just dl goes to theta. So this is kind of important so this theta shows up here in the dynamics. So what happens if theta goes to infinity, essentially, okay? So the breakup rate is doesn't go to 0 fast enough. And in this setting, you cannot really study that, it turns out. So I don't want to give any more details. So we want to look at a different way of studying the same thing. And what we did is we don't embed our empirical measures in the actual type space. So this is not centered at x, but we center it at the mass fraction. Okay, so this is another way of looking at the system. We throw away the information of space completely. Okay, good. So, and then we can do the same exercise in a sense, and we end up with a measure value process. Let me spare you this. So we take a different embedding and look at a different way of looking at the process. Still, we get a measure valued process in the limit, and it's again a measure value diffusion process. And if I test this, wait a minute, it should come here. Here. So it has the same structure as the one before. But it's not a Fleming-Muir process. So this is a technical difference because this resampling part is not of standard Fleming-Muir type. So the resampling should always look like in the previous process, but it doesn't look like that here. But okay, you can deal with it. But the mutation part is again very similar. So you can think about this. A is a generator of the dynamics on 0, 1. Okay, so this is a very simple diffusion process. That has a Wright-Fisher diffusion part, it has some drift here, and it has resetting to 0. But essentially, what this can tell you, if you look at a particle that has this generator on 0, 1, so then you have this duality relation that comes for free from the derivation. So if you want to study the time evolution of in expectation of your random measure tested against H, then you can simply study a particle on 0, 1. That's very simple. Okay. It should be possible to lift, so for standard Fleming-Muir, you can lift this to higher order dualities, because there the resampling mechanism has a generic form. Because it doesn't have this generic form here, it's not clear at this point how you could lift this to higher order dualities. It should be possible, but we don't know how it works. Okay. Good. So at least in expectation, you can study the evolution of your measure value process with a single dual particle. And you can also show that, again, this is equivalent to the same process if you map this onto this simplex, ordered simplex of mass distributions. Good. Now, main motivation was, okay, we want to look at dl goes to infinity as well. And so here the breakup rate is a bit larger, and so we have more clusters, and we will get a different behavior in the limit. Let me skip this part. So you can do this in 2 steps. This is what I explain here. So you do first this and this. We do it directly now. I only talk about the direct limit. So we rescale the masses on the scale we already know is going to be the right one in the stationary measure. So they won't be on scale n, but they will be on scale d. So I multiply essentially eta x by d here, where I center my drag measures. And then you throw in a factor, essentially L over n is 1 over rho. You do that so that the limit will be independent of rho. Okay? You don't have to do that, but then your generator will contain rho as a variable, but it doesn't have to if you simply look at mass fractions, essentially. So it's nicer to do it that way. And then you do the same thing again. You will have to slow down your process this time. Otherwise you get diverging rates, but it's the same thing. And the interesting thing is now that if you compute the Carré-Duchamp for this one, because you have a different scaling and you have to slow down your process, Carré-Duchamp will go to 0. So this is going to be a deterministic limit process. Okay, and it still has the same structure. So this mutation part will be a diffusion on 0, 1, and the only thing is that the Carré-Duchamp goes to 0. So therefore you don't have a diffusion process, but you have a deterministic process that is simply given by this the mutation operator. And good. So and then of course this duality is much stronger here now, because then really mu t itself it's a deterministic measure now. It's no longer a random measure. So this, if I test it, will be a deterministic object, and it is really equal to this expectation of the dual particle that evolves according to this a bar, right? Let me remind you, a bar is very simple. It's a diffusion with drift and resetting. It's always of this type. Okay, no, it's the wrong way. Good. Yeah, and because it's so simple, you can even solve this explicitly. So you can get, of course, you use Dünken equation. You can get a differential equation for this mu th, and then you can turn this into a Fokker-Planck equation. Because of this resetting mechanism of the dual particle, essentially it shows up independently of where it is. It jumps back to 0 at rate 1. This gives you a boundary condition for your for your density at 0, x equal to 0, which is 1. And you can solve this explicitly. There's a time-dependent solution you can derive, which is a lengthy formula, but it's not so important. And it will converge to the stationary distribution, which was the exponential one, which we showed you for the stationary result in the very beginning. Okay, and you can even start with mass that is on higher scale. So if you put all your particles in one site, so you have a single cluster of mass n, and you can start with this as an initial condition. So on the scale 1/d, there's nothing. So essentially, you don't start with a probability measure, but with a sub-probability measure, and then you see how the mass shows up on the right scale here from this equation. So you can include higher order scales. Good, and this is just a solution to this Fokker-Planck equation compared to a simulation. Okay, and it works pretty well. And this is the stationary thing, is the exponential distribution. And we started with the piles on this particular mass scale. Okay, a single pile here, and then we evolved the system. Okay, and the green thing is always the stationary distribution, and the black stuff is the numerical solution to, well, you have an exact formula, so it's the solution to the Fokker-Planck equation, and the histogram is from a simulation. Okay, good. So let me simply, and what is one interesting point, so we have now a scaling limit for the inclusion process dynamics on all scales for the breakup rate, and if you write your embedding correctly, then the limits even don't depend on the density, which is explained in some detail here, but I don't want to go into that. Okay, thank you.
Thank you. So are there any questions for this last talk?
Yeah, I'm just curious about the one-dimensional process. Like, to what extent the totally asymmetric property is relevant? Like, let's say if we, as far as I understood, it's totally asymmetric, right?
No, it was symmetric.
Ah, it was symmetric.
It was complete graph, even, the dynamics.
Okay, even in one dimension.
No, complete graph means the dynamics was really, I have a completely connected graph. Everybody can jump everywhere. But the stationary part of the talk also works for asymmetric. It has to be spatially homogeneous dynamics. Could be asymmetric in any dimension.
So, really nice talk. What about if you start with the stationary translation, so uniform distribution in your graph, and you look at the show of the clusters? Do you have a characterization of the dynamics? If the first cluster?
Yeah, that's a very interesting question. So, yes, so you could, an initial distribution for this thing would be delta 0, tells me, if I go back to this, to this, let's look at this. So this is an interesting part. So what happens if your mass is homogeneously distributed, take a Poisson density rho, right? So then you have nothing clustered at the initial condition. And then the question is, how does it arise? So what we know from this, in fact, we know that our measurable process is equivalent to this Poisson-Dirichlet diffusion. And for this diffusion, they have also studied this type of initial distribution. And you know that for any positive time, you have all the masses immediately clustered. Okay. And then the question is, can you propagate backward in time maybe some initial condition? But what is the distribution of these clusters at time 0? And we were, I think, essentially, it doesn't exist, this kind of entrance law, because what you can think about it from the dual particle. It means if you start with delta 0, this equation will tell you, okay, the initial condition for your dual particle is to be at 0 with probability 1, and then instantaneously it will be somewhere because it has a positive drift here, right? And then it starts diffusing.
Yeah, but this microscopic time 0 plus.
Yes.
You have already the biggest cluster, what it will be at the end, or?
Yes. So what you can also do is you can look at a different time scale and study the microscopic dynamics from order 1, and then there are other results that help you kind of to understand how they grow. But I don't think you can kind of match them together in the sense that there will be a, if I tell you that, so you're asking if there is a mu0 plus measure here that has a particular distribution, and I thought so that this is the case, but now I think maybe not. I mean, there are other processes that come out from infinity. If you look at these, how they, calculation, no, what are they? Coalescence. Okay, coming down from infinity. I think you also, this is similar here. Okay? So you will not really have an initial condition mu0 plus.
Thank you.
Any other question? So if not, we can give a round of applause.